I'm Sam, a PhD student at UC San Diego. I'm presenting an experience report today um, with my colleagues at Berkeley about our experiences teaching data science courses together. When we first got together to teach data science courses, there was a clear divide between the CS people, the computer science people, and the people from statistics. People from computer science were used to teaching things like Python, big O notation, and a difference between disk and memory. The stat people, on the other hand, were used to teaching things like simple random samples, confidence intervals, and bias versus variance. But if you put these two people together to teach a data science course, we might wonder, what would they agree on or disagree on? In other words, what do CS and stats instructors need to negotiate when they teach data science courses together? We experienced this question firsthand when we taught a course together called Data 100. Data 100 is a second or third year course for undergraduates at UC Berkeley that covers a broad array of topics like Python programming, data viz, and modeling. We created this course in spring of 2017, and it served over 2,500 students this past year. Over the past years, we've had a lot of discussions and sometimes debates about what to put in the course. I'll share 3 specific case studies about discussions that we've had while deciding what to put in the course and how much to emphasize the topics that we cover. In the first case study, we answer the question, do we need to delve into algorithms? In the second, we discuss how to approach statistical modeling. And in the third, we discuss how to approach real-world data. My goal is to give you a preview of conversations that you might encounter when you teach data science courses with other people. The first case study talks about algorithms. Algorithms have a big part to play in teaching data science. One particularly useful algorithm is gradient descent, which we use to fit all kinds of models, ranging from simple, like linear regression, to complicated, like neural networks. But when it comes to teaching gradient descent, we ran into the problem of at what level of abstraction to teach it. For instance, we could have students simply use a package that completely implements the model and the gradient descent algorithm. Another alternative is to have students implement everything by writing their own version of gradient descent from scratch. And a third approach is a hybrid of the two, where students implement some of the model and use a package for other parts of the algorithm. But of these approaches, which was the best for our students? Within our group, the stat instructors tended to prefer using a package like scikit-learn, where students could call a function and the package would do everything internally. The comp sci instructors tend to prefer having students implement the entire gradient descent algorithm from scratch. I'll present to you a condensed version of our dialogue. The stats instructors tend to point out that when it comes to real data science practice, we almost never use our own implementation of gradient descent. We use versions that packages already implement because they're already optimized and debugged. Why should we teach students to implement gradient descent themselves? Here, comp sci instructors pointed out that teaching gradient descent is a useful place to start talking about trade-offs that we encounter in data analysis. One such trade-off is the trade-off between runtime and accuracy. On large datasets, gradient descent can take a long time to finish. If we stop gradient descent short, we can cut down on the runtime of our algorithm, but it makes our models less accurate. Trade-offs like these appear all the time in data science, so it's useful to point them out when we can. And in this case, gradient descent points to a key trade-off that we often make. To this point, stats instructors said, why can't we just use pseudocode to teach these same trade-offs? Why do we need students to implement gradient descent in real code? In response, the CS instructors noted that writing code helps students understand algorithms more deeply. Understanding algorithms more deeply, and especially in the case of gradient descent, is important because even when it comes to reusing a third-party implementation of gradient descent, the data scientists need to tune parameters of the algorithm, like the learning rate in the case of gradient descent. And to really develop that understanding, it helps to have students implement the algorithms themselves. So we resolved our discussion by having students implement a simple version of gradient descent in class and as part of their assignments. But for the rest of the course, students mainly used a package like scikit-learn to fit their models. Importantly, we didn't want to use a hybrid approach because that involved introducing yet another package that students would have to learn. In the second case study, we discussed how to approach statistical modeling. Models are widely used in data science. For instance, we could fit a linear model to predict a person's shoe size given their height. When teaching models like these, we have, again, several options of teaching approaches. For instance, when we teach linear models, we could start by jumping straight to the formulas for the model parameters. A more advanced way to present this would be to start by defining a loss function, which measures the difference between our model's predicted values and the true values. We can then derive the formulas for the model parameters by minimizing the loss function. So in this case, we could derive the formulas for the slope and intercept of a linear model. An even more advanced step would be to start with a likelihood principle, or maximum likelihood estimation. By using maximum likelihood estimation, we can derive the loss function, which in turn derives the formula. But this approach led to some debates among our staff members. The CS instructors preferred to use loss functions to teach modeling instead of maximum likelihood estimation, while the stat instructors preferred to use maximum likelihood. The CS instructors asked, why do we need to use maximum likelihood to derive these complicated formulas when we can use gradient descent instead? Formulas using likelihood can get complicated pretty quickly, and I'm not really too sure what the benefit is for students. In response, the stat instructors said, when using the likelihood principle, we can show how the assumptions we make affect the model. For instance, by changing the assumptions we make about the model, we can also derive other important models like weighted regression or the generalized linear model. This was convincing, and we could all see the importance of using likelihood. At the same time, the CS instructors pointed out that in the class, students felt unprepared for likelihood. We didn't require a probability course before Data 100, and so when students encountered likelihood for the first time, they really struggled with the concept. So we decided that we could teach likelihood in a future class, and instead include the stepping stones to likelihood in this class. So in our class, we decided to start with loss functions and use loss functions to derive formula for simple models. Importantly, we can also use a variety of loss functions and talk about when the domain informs our choice of loss functions. So for instance, if for a medical test, we really don't like false positives, but we're okay with false negatives, then in that case, we could choose an asymmetric loss function. And we decided to postpone likelihood to a more advanced course in the curriculum once students had more math background. Instead, we included the stepping stones to using the likelihood principle in our course, like using expectation and variance. In the third and final case study, we discussed how to approach real-world data. In a typical introductory stats class, we'll talk about the ideal random sample, where if we're trying to estimate the number of people in the US who have COVID, for instance, we could take the population of people in the US, apply a random sampling scheme, like using a simple random sample, to get a sample of hospital visits. One common teaching method is to use this opportunity to introduce sampling schemes like the simple random sample and the stratified sample, and then start having students do probability calculations on these samples. Using found data is a common practice in our data science courses because many data sets we find online are found data. For example, tweets or emails are both examples of found data since they're collected in a non-random way and they weren't designed for a scientific experiment or study. The stats instructors prefer to talk about random samples. whereas the CS instructors prefer to use found data and not worry too much about whether the sample were collected according to a random scheme or not. This raised problems among the stats instructors, who mentioned that random samples are representative of the population, and when a sample isn't collected according to a random scheme, it's hard to make inferences from the sample back to the population. There are many cases in real-world practice where using a non-random sample, like phone calls, results in a wrong conclusion, like predicting the wrong presidential election winner. In response, the CS instructors pointed out that few datasets are truly random in practice. Even if you design the best sampling scheme, issues like non-response make your data not truly random. It can feel disconnected from reality for students if we focus so much on random samples when, in reality, they're going to go out and analyze non-random data. Nonetheless, the stats instructors pointed out that knowing the ideal scenario of having a perfectly random sample is useful as a comparison point against the data you do have, so you can begin to predict ways that your data might be biased towards one group or another. Since we could see the advantages of both approaches, we decided to use a blend of the two. We would talk about the ideal random sample in our class, but with reduced emphasis on the exact sample schemes and probability calculations that were there before. We will also point out the difference between the ideal random sample and found data, and discuss the trade-offs of using found data. For instance, when using found data could be problematic, and when using found data would be useful. So I presented a brief overview of the 3 case studies I wanted to show you today. Reflecting on these examples at a higher level, we might next ask, what do these case studies say about CS and Stats' overall approaches to teaching data science? One core difference between the 2 approaches is an analysis that focuses on inference versus prediction. For instance, an inferential analysis might ask whether income inequality is actually correlated with economic mobility in the population. This is a common statistical view, a view that cares about the covariates and what they say about the larger population. A predictive view, on the other hand, cares less about the model's parameters and more about the model's accuracy. For instance, we might care more about our model's ability to predict poverty and wealth, more so than whether the model's covariants are interpretable. This is a common view for computer science instructors. These approaches trickle down to other parts of the curriculum. It affects what datasets we choose and how we use our datasets, and it also affects the models we choose and why we select certain models over others. But rather than focusing on one approach over the other, we found it most useful in our course to try to incorporate both perspectives at the same time. So when we talk about inference, we'll also talk about prediction and vice versa. And in general, we found that many of our discussions end up improving our course when we more tightly integrate CS and Stat. Both CS and Stat have useful perspectives for nearly every topic in data science. For instance, the data frame, a common data structure that we use for analysis, was originally designed by statisticians, and we can compare and contrast the data frame with the relation, which was designed for use in databases. In real practice, when we do data analyses, we include both perspectives all the time. For example, writing code to remove missing values from a data frame actually has effects on our statistical analysis down the road. CS and Stat come up together all the time in data science, which leads us to conclude from our case studies that tightly integrating CS and Stats together makes data science courses more relevant to real-world practice. There's so much more I'd like to say about this topic, but I'm leaving out the presentation for the sake of time. Still, I think that these 3 case studies gives an inside look into the practice of teaching and working across traditional disciplines to create a data science course. And I hope that they spark reflection or new ideas for your course design. That concludes my presentation. Again, My name is Sam, and I'd love to talk more about your experiences teaching data science. Thanks.